those speed cameras and things. Okay. And then we could also look at the sonar. Okay. And then also to detect the moving stars and all of that. So all those are applications of Doppler effect. Question number 7, electrostatics. 2-point charges Q1 and Q2 are placed 30 centimeters apart along the straight line. Q1 is this, the point P is 10 centimeters. Okay. As shown, the net electrostatic force is 0. So F net is 0. All right, then define the term electric field at a point. Remember what we said? This is the electrostatic force, okay, experienced per unit positive charge placed at that point. Okay, you can just go back there and then you just read our definition. Electric field. All right, then state giving reasons whether the point charge Q2 is positive or negative. State giving reasons. Now, the fact that we're having 2 charges, one of which is negative, and then we have a net force of 0, then chances are high that this Q2 is going to be a positive. Why is it a positive? Because it needs to counter this negative force or the negative direction so that there is some sort of attraction between the forces themselves. Okay. So we're going to say that the electric force due in Q1 will be negative. No, not really negative, but the direction will be different, because if this point charge is positive, so which means the force applied here is going to be force experienced, that this is going to be to the left. And then if this is a positive and this is a positive, then the force is going to be to the right. There's repulsion and what. So that's why I'm going for positive. Okay. So explanation, we're going to say that since the E net is definite, electrostatic field is E, not F. Okay, so we're saying the E net is 0, E1 and E2. So E1 and E2 are in opposite directions. They have to be in opposite directions. All right, so that is that. Then I want us to calculate the value of Q2. So we have to use the electric field. So remember we said E is KQ over R squared. Okay. So I'll start with the first one, which is Q1. 9 times 10 to the 9 multiplied by 3 times 10 to the negative 9 divided by 10 changed to meters. That's going to be 0.1. I'll square this. Now, since we know that our E net is a 0, which means the E1 must be the same as the E2. Okay, let me simplify that. I'm having 9 times 10 to the 9. I'm multiplying this by 3 times 10 to the negative 9. This is over 0.1 squared. I'm getting 2.7. Okay, let me look at E2. E2 is saying it's going to be K, which is 9 times 10 to the 9, multiplied by Q2 over the distance. Now it's going to be 40 centimeters, which is now 0.4 squared. If I simplify that, I'm going to remove that, put a 4. Going to remove all of this. It's going to give me 5,625 times 10 to the 10 Q2. But remember, E-net is 0, so which means E1 and E2 have to be the same. So this is the same as 2.7. Divide both sides by 5,625 times 10 to the 10. So when I do that, I'm going to have 2.7 divided by my answer. Getting a weird answer. It's very weird. It's 4,8 times 10. 1, 2, 3, 4, 5, 6, 7, 8. Yes, it's negative 8 coulombs. Okay, or you can just give it to us as 480 microcoulombs. 480 times 10 to the negative, or 480 microcoulombs. Yes, perfect. All right, then 7.4 state coulombs law in words. Remember what we said? That's more like the definition of electrostatic force. We're saying the electrostatic force between 2-point charges is directly proportional to the product or to the product of the magnitude of the charges, but it's inversely proportional to the distance of separation, to the square of the distance of separation. Then calculate the magnitude of the electrostatic force exerted by Q1 on Q2. So we already have the Q1. Now we calculated our Q2, which is now 4,8 times 10 to the negative 8. So let's just get the force. Remember, the distance is 30 centimeters. So force, we said it's K Q1 Q2 over R squared. So 9 times 10 to the 9. This is going to be 3 times 10 to the negative 9. And then times 4,8 times 10 to the negative 8 over 30, which is 0,3 squared. And then I just get my force, punch this into the calculator first. 9 times 10 to the 9 times 3 times 10 to the negative 9 times 4,8 times 10 to the negative 8 again over 0,3 squared. That gives me something weird again. I hate this, mustn't it? So it's 1,44 times 10, 1, 2, 3, 4, 5 here. So it's negative 5. Remember, it's a force, so it's newtons. All right, then 7.6, we've been given point charges and they drew for us the field patterns. So 2 charges are now brought into contact with each other and then separated. So whenever this happens, after the separation, the 2 charges will have the same magnitude. And the same sign, which means we expect some bit of repulsion afterwards. All right, so with this one, they are telling us that a learner draws the electric field pattern for Q3 and Q4 after contact. Is the diagram correct? The 2 charges are now brought into contact. So, is it still connected to this? Yes. This is a negative 3. This is a positive 4,8. Okay, so if you combine this, let me just be sure, 4,8 times 10 to the negative 8, I'm saying plus negative 3 times 10 to the negative 9. Okay, I get a positive answer. I divide it by 2, so which means it's correct since the field lines are moving out. So the answer is a yes. Okay, because both charges are positive and equal in magnitude. All right. Then question number 8, which is electricity. So, and electricity, we just need to know about Ohm's law. Okay. How do we state Ohm's law in words? So the potential difference across a conductor is directly proportional to the current in a conductor at a constant temperature. So this is important. Then the directly proportional part is also important. So those keywords, at least they shouldn't miss in your definition. And then the relationship between current, potential difference, and resistance at a constant temperature for a simple circuit. You need to know that difference between ohmic conductors, those that obey Ohm's law, and then the non-ohmic that disobey Ohm's law. Then we solve the problems using this Ohm's formula for series and parallel circuits. We need to know the difference between the two and what happens in the series, because many times circuit diagrams are given and then we fail to notice what's happening. So one thing we need to remember is that for parallel circuits, the velocity, not velocity, it's the voltage, which voltage is also known as the PD, is always constant across. For series, is the current that is constant. Okay, then power energy, define what power is, rate at which work is done. This is the formula. And then the different formats of power, okay, right from there. Then solve circuit problems involving concepts of power, electrical energy, deduce that 1 kilowatt hour refers to that, calculate the cost of electricity, okay. And then the great 12 aspects of internal resistance, series and parallel, and then EMF also needs to be understood quite well, okay. How do you define EMF? And so on and so forth. Okay, so let's just focus on this electricity, then we shall come back for electrodynamics. Okay, so 3 results.